Okay, welcome AP Chemistry students. We got a new unit we're starting here, and this one is about thermochemistry. A lot of this is going to be new in the sense that we did not cover it last year in chemistry class. Now, if you've had a physics class, then a lot of this will probably be reviewed for you. But basically, we're going to start talking about the energy of chemical reactions and how all of that works. And we're going to do some things with heat and some things with kinetic and potential energy and work and those sorts of things. So again, concepts that should be fairly familiar to those of you who've had physics. And those of you who haven't, you should be able to pick up on this fairly quickly. Now, I'm going to fly through this. I'm going to try to fly through this because there's a lot here. But to be honest with you, there's not a lot of this that's on the AP exam. They expect you to have this background of information, this background understanding of it, but as far as asking actual questions about this stuff, they usually don't. So try to keep up. You've got some blanks to fill in, and I'm going to move pretty fast through here. Okay. So energy, the definition in chemistry we're going to use is the ability to do work or transfer heat. Okay. One of those two things. Work is energy that moves an object. Okay, if you don't move something, you're not doing work. So I can push on a wall all that I want, but by the science definition, even if I completely exhaust myself doing it, I'm not doing any work because I'm not moving the wall. Okay, and then heat is the energy that causes the temperature of an object to rise. So you add heat to something, its temperature goes up because it's the average kinetic energy of its particles increases. The particles start moving faster on average. Okay, potential energy versus kinetic energy. This is very basic stuff that you've talked about a long time ago. Potential energy is the energy an object has based on its position. Okay, so the classic example is something that's up high that could fall. That has a lot of potential energy. Potential energy happens when there's some sort of force operating on an object. So the force, usually it's two opposing forces, and when one of the forces gets removed, then that object can move. Okay, so for example, if you've got something up on a high desk and you remove the desk somehow, or if you move it off of the desk, then it's going to fall down to the ground because the force of gravity is acting on that book. But until the book got moved, the force of the table was pushing up on the book as well. Okay, and then kinetic energy is the energy of movement, and that's when something moves, it has kinetic energy. Okay, and the way that we figure this out, this formula is kind of important for this section, but again, they don't usually give you a lot of problems related to finding the kinetic energy of particles. We will get into a little bit of that in a later unit, but for now, basically you just need to know that this is mass times velocity squared. Okay, so the mass of something times the square of its velocity, that's going to give you kinetic energy. Right? Something that has a bigger mass, when it's moving at the same speed as something that's smaller, is going to have more kinetic energy. But the square of the speed is, it ends up being more important how fast it's going rather than how massive it is. Okay, SI unit of energy is the joule. And 1 joule equals 1 kilogram times meter squared over second squared. Okay, but again, you don't really need to know that. You just need to know joule is the SI unit of energy. We use joule a lot in this unit and a couple other units in this class. The calorie is another unit of energy that you're probably very familiar with. This is the one that they put on cereal boxes. All the food labels at the store tells you how much energy you can get out by consuming that particular food. And the way they figure that out is by burning it, actually. We'll talk about that more in a couple of days. 1 calorie equals 4.184 joules. Okay, now the calories that you see in the grocery store, in case you're interested, are actually kilocalories. Okay, so if something says it's 100 calories, technically it's 100,000 of these calories. That might be depressing to you, but that's the truth. Just so you know that. System and surroundings, the difference between that, basically a system is whatever you decide that you want it to be, okay? So if I decide my system is the classroom that I'm standing in right now, the surroundings is everything else in the universe besides this classroom, Okay, if you decide that your system is a beaker of water, or a solution of sodium chloride that you have in a beaker, then your surroundings is everything in the universe besides that beaker. Okay, and so that's just definitions that we use there so that we can differentiate between what's happening to the system and to the surroundings. Because usually what's happening to the system, if energy is going into the system, then energy is flowing out of the surroundings and vice versa. Whatever's happening to one is usually the opposite of what's happening to the other. Okay, work. That is the energy that it takes to move something. We already talked about that. Now the actual equation for work is force times distance. Okay, so force is in newtons, distance is in meters typically, and that gives us work in joules. Alright, so here's an example problem here. The movement of water from the ground through the trunk to the upper limbs of a tree is an important biological process. What part of the system, if any, undergoes a change in potential energy? Okay, and so what's happening here, and the answer is part of the system does undergo a change in potential energy. It's the water, okay? So the water undergoes a change in potential energy as the water moves up the tree. Its potential energy is increasing. Okay, next part here is work done in the process. Okay, well, we moved something. So, I mean, that's really the only question you have to ask if you're deciding if work gets done here. So, yes, work is done in the process because we moved the water. Or, we didn't move the water, because the water moved. Okay? Anytime something gets moved from one place to another, work is done. Alright, transfer of energy here. So this picture is hard to see. I think it's probably hard to see on your note packet too. But what's happening is you've got a lot of potential energy with this clay ball on top of the brick wall. Okay, because of its position. Gravity is pushing down on it, but the brick wall is holding it up. Okay, now as soon as the ball moves to the edge and starts to fall, now it doesn't have a force pushing up on it, so the only force acting on it is gravity, and it starts to fall, starts to move. And because it's moving, now it has kinetic energy. Okay, so it has only potential energy up here at the top. Okay, and then here the potential energy is being converted into kinetic energy, and then down at the bottom, once it stops, it now no longer has kinetic energy. Its kinetic energy falls to 0. Okay, so some of the energy, that kinetic energy that was in it, is actually used to flatten the ball, to do some work on the ball. Okay, so now the ball is a different shape than it was to begin with, and the rest of the energy, that kinetic energy that was there, we lose it as heat to the environment around it. Okay, and so that's the transfer of energy here. So it starts out as potential energy up here, and then it starts to get transferred into kinetic energy, and then when it hits the bottom, we do some work on the ball, and we have some heat released. Okay, so that's how that transfer works. Alright, so here's a sample problem there. Bowler lifts a 5.4 kilogram or 12-pound bowling ball from the ground to a height of 1.6 meters, and then drops the ball back to the ground. Okay, so what happens to the potential energy of the bowling ball as it is raised from the ground? Obviously it increases. Okay, and let me check the next couple of problems here. Okay, so the next question is what quantity of work in joules is used to raise the ball? So then we want to actually calculate our work, and work is force times distance. So the force, it's a 5.4 kilogram bowling ball. Okay, and so we didn't really talk about this, but force equals mass times acceleration, F equals ma. And again, if you were in physics, you that you would know this, okay? But I don't expect you to know this necessarily in chemistry, because again, these types of problems don't typically show up, but I'm showing you something here. So we've got 5.4 kilograms, and we multiply that times the acceleration due to gravity, which is 9.8 meters per second squared. And when we do that, uh-oh, my calculator's out of batteries. Oh man, I'm in big trouble. Oh, okay, thanks. A student who is my TA, whose name I cannot say because this video is going on YouTube, saved the day. So thank you, unnamed TA and first hour student. Because I can't do anything without a calculator. We all know that. Okay, so what we're going to end up with here is about 53 newtons of force. Okay, so now I've got my force, 53 newtons, provided that I did that correctly, times the distance, which again we want that to be in meters in order to get our work in joules. So 1.6 meters here. So when we multiply that by the 1.6, we end up with 85 joules of work done. Okay? And then it says after the ball is dropped, it gains kinetic energy. If we assume that all the work in part B is converted into kinetic energy at the point of impact, what is the speed of the ball at the point of impact? All right. So what we just figured out, 85 joules of work was it took 85 joules of work to lift that ball up to the height that it was at. So assuming all of that gets converted, I just forget that number, 85. Wow. 85 joules equals, now we got to remember the formula for kinetic energy here. Kinetic energy equals 1/2 mv squared. Okay, so 85 joules equals 1/2 times the mass, which was 5.4 kilograms. And then we want to know the speed of the ball at the point of impact. Okay, so v squared. So then we're just going to solve this thing for v. V squared is equal to, let's see if I can do this quickly. Uh, 31.5 or so. Let me take the square root of both sides here. Our velocity should equal 5.6. Sig figs here, so 5.6 meters per second when it hits the ground. Okay. All right. So that's some examples of transfer of energy and how that works. Law of thermodynamics. First law of thermodynamics. We're going to talk about the second law in a couple of days. It says energy is not created or destroyed, and that kind of goes along with the transfer of energy thing we were just talking about. Okay. When you got that clay ball up on top of the brick wall there. All of the potential energy that is there is going to go into work or heat finally when that ball hits the ground. Okay, none of that energy is created or destroyed. It has to go somewhere. Okay, and so you can have two different scenarios here. If you've got your system right here, and if the energy of the system decreases, okay, then that means that the energy of the surroundings actually increases. This energy gets lost to the surroundings. Or your other scenario here, if this is your system, you can put energy in from the surroundings, and then the system gains energy. Okay, so it usually flows from the system to the surroundings, or from the surroundings to the system. Total amount of energy in the universe is constant. And again, this is excluding nuclear reactions. But we already talked about the system and the surroundings here. Okay, now the internal energy of a system, if you add up all of the kinetic and potential energies of all the components in the system, that is the internal energy. Okay, very difficult to figure out the internal energy of a system because there are so many different parts to it. Okay, but if you add all of that stuff up, so if we've got a beaker full of a solution of sodium chloride, okay, and we added up the total energy of all the components in that system, the moving parts and everything that's in there, and the bonds that are formed there and the energy of those bonds and all of that stuff and the the electrostatic interactions, all of those things, that would be the internal energy of that system. Okay? To find the change in internal energy, that's a little bit easier to do. If we know, if we can figure out our final minus our initial energy, internal energy, then we can find the change. Okay? And again, that's a little bit easier to find than the absolute energy. So changes in internal energy, if the change in energy is greater than 0, that's for the system. Okay, so if the system we're looking at, if that change is greater than 0, then that means that the final energy must be greater than the initial, so that means the system gained some energy from the surroundings. Some energy flowed into that system. Okay, and that energy change is called endergonic. I don't think you need to know that term. I've never seen it on an AP exam, but it's in the book, so there you go. So if we've got the opposite happening and delta E is less than 0 for the system, then that means some energy must have gone out of the system into the surroundings, and that's called exergonic. Okay. So when we do an exchange of energy from the system to the surroundings, or from the surroundings to the system, whichever way, it's going to be as heat or as work. Okay, so either work is done on system or surroundings, usually to compress it or expand it or that sort of thing, or heat is transferred between the two. Okay, those are the two types of energy transfers that we usually deal with in chemistry. All right. So another way to say that is delta E equals Q plus W. Okay, delta E, that's the change in internal energy, is equal to the heat change and the work change. Okay. So that just the convention here of how this works. When we're talking about Q, which is heat, okay. If it's a positive Q, that means the system is gaining heat, okay? If it's negative, so if it's positive, the system is gaining heat. If it's negative, the system is losing heat, okay? For W, if the W is positive, it means work is being done on the system, okay? So if you do work to the system, that means that you're putting some energy into the system, okay? So that's going to be a positive energy change. And then a negative means there's work done by the system on the surroundings. The system is doing some work to the surroundings, which means it's transferring some of its energy to the surroundings. Okay. For delta E, if it's positive, that means there's an overall energy gain by the system. And if it's negative, it means there's a net loss of energy by the system. All right, so here's a sample problem. And this is getting a little bit closer to something that you might actually have to do. We've got hydrogen and oxygen gases in a cylinder with a movable piston. Okay, I am horrible at drawing things. Let's see if I can do this here. So you've got this cylinder, okay, and inside the cylinder you've got a piston that can move up or down, okay. And this piston's adjustable, and let's say you've got some hydrogen and oxygen gas inside of here, and so you can move the piston either direction, and that will actually allow the gases to expand, or it will cause them to contract. Okay, so this is our system right here in this particular example. As the reaction occurs, it says the system loses 1150 joules of heat to the surroundings, and the reaction also causes the piston to rise as the hot gases expand. Well, see, I did mine backwards, because it's actually they put the piston at the top, and so that's causing the piston to go up. Here, let me redraw it so that it actually fits what they're saying here. Okay, so our piston's up here on this one, and the gases are down here, okay? And so what's going to happen is these gases are going to push up on this piston, do work on it as they expand, okay? So we got to figure out what's the change in internal energy of the system here. Delta E equals Q plus W. And the heat change here. The system is losing heat to the surroundings, okay? So what that means is we need to make this a negative Q, okay? Negative 1150 joules okay? Because it's losing heat to the surroundings. And then we're going to add that to the work done, okay? The expanding gas does 480 joules of work on the surroundings. So 480 joules of work done by the system on the surroundings, that's also a negative number, okay? Because the energy is flowing into the surroundings out of the system. So plus a negative 480 joules, okay? So our delta E here, overall, the system loses energy when this happens, okay? Which makes sense. Usually when we're talking about a combustion reaction, it's going to give off heat and energy into the surroundings, and so it's going to be an exothermic reaction. Hopefully you guys remember talking about that last year. Negative 1150 plus negative 480 gives us negative 1630. And that's our overall energy change. So what that tells us is, because it's negative, it means that energy is flowing out of the system into the surroundings. Okay, exchange of heat between system and surroundings. So heat specifically is what we're talking about now. And these terms you should be more familiar with. Endothermic and exothermic, okay? If the surroundings give heat to the system, that's endothermic, okay? And we'll talk about delta H in a couple of days. You don't have to worry about this delta H thing yet. But delta H is almost the same thing as Q, okay? So it deals with heat. When heat is released by the system, that's called exothermic, okay? So the heat's released by the system. That's an exothermic process, and that means the system is losing energy. Okay, and last thing we need to talk about here is state functions. It's just too hard, like we were talking about earlier, to find the total internal energy of a system. There's just too much going on there, too many different factors that affect the energy of the system. So to try to figure that out is too complex. But here's something that helps us. We actually know that it doesn't, this is where I'm going to get a little philosophical here, okay? The destination is the important part. The path you take to get to the destination is not the important part. In chemistry, at least, okay? And actually not always in chemistry, but for state functions, that is true, okay? So I'll sort of explain what that means in a second, okay? But the idea here is this water in the middle is at 25 degrees Celsius. Now, I could have gotten there by cooling down from 100, or it could have gotten there by warming up from 0, okay? Either way, it is now at 25 degrees Celsius, okay? So it doesn't matter so much, if we're talking about state function, how it got there. It just matters that it got there, okay? So internal energy is a state function, okay? It depends only on the present state of the system, not the path by which it arrived at that state. Now, let me give you an example of this that this sort of helps me. What this means here is delta E. You can find that using the final and the initial energy, and it doesn't matter what detours it may have taken along the way to get there, okay? And so that's why that's actually a fairly simple thing to find. Okay, so here's the analogy. If you're going from Chicago to Denver, Chicago has an elevation of 596 feet above sea level. Denver has an elevation of 5,280 feet above sea level, okay? Altitude is an example of a state function, okay? Because what that means is if you're going from Chicago to Denver, say Denver's over here, Chicago's over here, okay? If you go this way to get to Denver, your overall altitude change is still exactly the same as if you just go in a straight line from one to the other, okay? It doesn't matter which way you go, your overall altitude change is the same. Now, distance traveled is not a state function because this is obviously a much shorter distance, this way right here, than taking this long roundabout path this way, okay? So distance is not a state function. Distance does depend on the path you take to get there, but altitude doesn't, okay? And in that sense, internal energy is sort of like altitude. It doesn't matter what chemical reactions you do along the way, whether you do a cooling or a heating process. If you end up in the same spot, then all you need to worry about is your initial energy and your final energy, and that's all you really need to know, okay? Now, Q and W, heat and work, those are sort of like the distance in that last analogy. Those are not state functions, okay? So here's an example of that. If you are going to discharge a battery, there's two ways you can do that. You can use the battery, like with a fan or an iPod or something like that, until it runs out of energy. Or you can short circuit the battery and you can drain all the energy out of it that way, okay? Now, the energy change for both of these batteries is exactly the same. The total overall energy change for both of these is exactly the same, okay? Because it's the same type of battery with the same beginning amount of energy and the same ending amount of energy. Now, the path that you take to get there does matter for Q and W, okay? In the short circuit example, when you're shorting out the battery, all of that energy gets lost to heat, okay? But if you're actually using it to run a fan, then some of that energy gets lost to heat, and some of that energy is used to do some work, okay? So overall, the total energy change is the same, but the Q and the W are not the same, okay? Here, the Q is much larger than over here, okay? And there is no work component on example A, okay? All right, well, we got through that faster than I thought we were going to. Again, this stuff is it's important background information for you to know. The stuff we're going to cover in the next few days is really the most important stuff that you know, because that's the stuff that you're going to see questions on the AP exam. Okay? All right, we'll see you next time.